Okay, let's dive in. We're taking a deep look today at something that, well, really set the tech world buzzing just a few days back, that big Google Cloud outage on June 12th, 2025. We've been sifting through the analysis expert takes, even chatter from folks inside Google Cloud.
Yeah, that's right. And our goal here really is to get under the hood. We want to understand, what exactly went wrong. Why did what seems like a relatively small technical glitch have such a massive global impact? Who felt it the most? And critically, what are the lessons here for cloud providers? Sure, but also for users, for, everyone relying on these services.
And it's that contrast that's so fascinating, isn't it?
Mhm.
The sheer scale of the outage versus, well, what sounds like a surprisingly simple trigger. You almost expect something huge, right? A cyber attack, maybe, or some giant hardware meltdown for something this big.
Exactly. But this one, it points to something maybe more fundamental, almost like a basic coding oversight, which kind of highlights potential vulnerabilities if the right checks aren't absolutely nailed down. It really shows how vital those robust safeguards are in these incredibly complex systems.
Okay, so paint the picture for us. What actually happened on June 12th? How did it start?
Right. So it kicked off around 10:51 a.m. Pacific time. An automated policy update started rolling out. Pretty standard procedure, usually.
An automated update. Okay, sounds routine enough.
Yeah, you'd think so. But this specific update, it accidentally introduced blank quota fields into a really critical internal system. It's called service control. You can think of service control as like the central nervous system for Google Cloud. It manages permissions, API calls, quotas, really core stuff.
Blank quota fields. So this vital system suddenly got input it wasn't expecting, like missing data where it expected a value.
Precisely. And that's where things went wrong technically. Those unexpected blanks triggered a specific bug, a null pointer error. It's like the software was told to look in a memory location for data, but the location was empty, it was null, it didn't know how to handle that, panicked, essentially, and crashed.
Ah, okay. Like trying to use a variable that hasn't been initialized, but happening at a massive scale.
That's a good way to put it, yeah. And this null pointer error, it caused the API management binaries, think of them as the traffic controllers for service-to-service communication. It caused them to crash. And the critical part, this wasn't just in one place. Because of how these systems replicate data, it happened globally, almost all at once.
Wow, global crashes for the API managers. That sounds foundational. What did that immediately break across Google Cloud?
Oh, it had huge ripple effects. Because service control and API management are so fundamental, their failure knocked over other core systems like identity and access management, IAM. That's what checks who you are and what you can access. So when IAM and service control stumbled, it impacted, get this, over 70 other Google Cloud services that depend on them. We're talking major stuff. BigQuery, Cloud Storage, Vertex AI for the AI folks, Cloud Run, the list goes on. Basically, anything needing authentication or quota checks was in trouble.
Right, that explains the sheer breadth of the impact then. So many different services affected.
Okay.
Let's talk timeline. Once that update went out, how fast did Google realize something was wrong? And how long did the fix actually take?
Well, the internal monitoring was incredibly fast. Alarms started going off within just 2 minutes of the policy update deploying.
2 minutes from rollout to detection.
I
That's
mean,
actually really quick.
it is, and they diagnosed it quickly too. Engineers pinpointed that null pointer error as the root cause in just about 10 minutes. So, roughly 12 minutes after it started, they knew what was wrong and why.
Okay, so identifying the problem took minutes, but people experienced the outage for, well, hours. What caused the delay in getting things back up?
Right. So mitigation efforts started fairly soon after, maybe 40 minutes in, but the recovery was the long part. Getting everything fully back online, especially in the main regions, took nearly 3 hours. The main issue during recovery was what they called cascading restarts, or a herd effect. Imagine all these crash systems trying to reboot and reconnect simultaneously worldwide. It just overloaded the recovery infrastructure itself, slowing everything down.
Ah, so it wasn't just fixing the initial bug, but managing the stampede of services trying to come back online all at once.
Exactly that. The sheer volume overwhelmed the recovery mechanisms.
Okay, so we know Google's own services like Gmail and Drive had issues. What about the big external customers? Who else really felt this?
Oh, the list is long and includes names everyone knows. Spotify, Discord, Shopify, Snapchat. They all rely heavily on GCP and reported major problems. Also, big AI companies like Anthropic and OpenAI, plus infrastructure players like Cloudflare and streaming services like Twitch, huge impact.
Wow, that's a significant chunk of the internet right there for a lot of people.
Yeah.
And we saw the reports flooding in, right?
Absolutely. If you looked at Down Detector, it just lit up tens of thousands of reports. I think the numbers mentioned were around 46,000 for Spotify, maybe 11,000 for Discord, about 10,000 for Gmail-related stuff. It clearly shows how immediate and widespread it was for users.
Really brings it home. Which
Yeah.
takes us back to that core question. How does something seemingly small blank quota fields in an update trigger a null pointer that then just cascades into this global meltdown affecting Spotify? Where was the vulnerability?
Yeah, this is when we get into the missing safeguards. The analysis points to a couple of key things. First, and maybe most critically, this specific code update wasn't put behind a safe feature flag.
Okay, hang on. Feature flag, can you quickly explain that for folks?
Sure, think of it like a dimmer switch, or maybe an on-off switch, for new code. You deploy the new code, but it's initially off thanks to the flag. Then you can turn it on gradually, maybe for internal testers first, then 1% of users, then 10%, and so on. It lets you test changes in production safely. If something breaks, you just flip the switch off, affecting only a small group. In this case, that mechanism wasn't used. The change went live everywhere, instantly.
Got it. So no safety net, no gradual rollout there. What about the code itself? Was there an issue there too?
Yes, that's the second major point. The code lacked what we call robust defensive error handling. Specifically, it didn't properly check for or handle the possibility of getting a null value, that blank field. Instead of, say, logging an error and using a default value or just gracefully skipping that data, it encountered the null and just crashed hard.
So it wasn't designed to be resilient if the input data wasn't exactly perfect.
Exactly. It wasn't defensive enough. And the final piece of the puzzle, how it went global so fast, was the rapid replication of that faulty policy data. The configuration with the blank fields was pushed out, and systems in pretty much every Google Cloud region pulled down that bad config almost immediately, triggering the same crash everywhere.
Right, that replication explains the global scope. So Google's obviously looked hard at this. What are they actually doing now to stop this kind of thing happening again?
They've outlined several concrete steps, really focusing on process and code resilience. First, stricter enforcement of using feature flags. They're saying all new code paths, especially for critical systems, must use flags and be validated in staging before going global. That directly addresses that first vulnerability.
That sounds absolutely crucial. Big lesson learned there.
Definitely. Second, they're improving defensive coding practices, especially in service control. Adding more rigorous null checks, better error handling, making it tougher. Third, they're rolling out a tiered rollout policy. Changes to services with a high blast radius, meaning if they fail, they cause huge knock-on effects. Those will get rolled out even more cautiously in stages.
So extra layers of protection for the really critical stuff. Makes sense.
And finally, they're also working on external communications during incidents. Things like better automatic alerts, making sure the status dashboards themselves stay up even when core systems are wobbly, and just being more transparent during an outage.
Those communication improvements are huge for customers trying to figure out what's going on. Okay, let's pivot this. What should cloud customers, big companies, small developers, anyone using GCP or any cloud take away from this? What are the practical lessons for us?
Yeah, this is a really important part. This incident is a stark reminder, right? Even the giant cloud providers aren't infallible. They aim for amazing uptime, but outages happen. So you, as the customer, need to build resilience on top of their platform. The analysis highlights a few key things this outage really underscores. First, multi-region redundancy and failover. Because this was global, just being in a different availability zone in the same region probably wouldn't have saved you. You need systems designed to potentially shift workloads to a completely different geographic region, maybe even think about multi-cloud, though that's complex.
Right. Don't just assume being multi-zone protects you from these big systemic failures.
Exactly. Second lesson, plan for graceful degradation. What does your app do when a key dependency like IAM or an API gateway goes down? Does it just crash completely? Or can it maybe serve cached data, show a limited version, or at least provide a helpful status message? You want it to limp along, not just fall over.
Yeah, making sure it doesn't just show a cryptic error, but maybe core functionality still works or it tells users what's up.
Precisely. And related to that, monitor your dependencies. Don't just monitor your own app's code. You need alerts on the health of the underlying cloud services you rely on. Use the provider status info, but maybe have your own checks too.
Like monitoring the foundation your house is built on, not just checking if the lights work inside.
That's a great analogy. And one more. Actually practice your incident response for provider outages. Run drills. Simulate GCP having a major issue. Do you know how to trigger your failover? Does your team know the procedure? How will you communicate to your customers? Knowing the plan versus having actually rehearsed it under pressure is very different.
Run fire drills for cloud failures.
Yeah.
That makes a ton of sense. Now, zooming out slightly, there's also some talk around this about Google's internal culture. The source material mentioned discussions, maybe some controversy about code quality versus the pressure to ship features fast.
Yeah, that definitely came up. Discussions on places like Hacker News, Reddit that were referenced, they pointed towards this ongoing tension, perhaps, concerns that sometimes the push from leadership for rapid innovation and deployment might inadvertently lead to skimping on some of the really rigorous safety checks or deep testing.
The classic tech dilemma, right? Move fast and break things
Wow.
versus move carefully and ensure stability.
It really is, and Google acknowledged this aspect. They've stated they're actively working to reinforce their engineering culture. A big part of that is making sure engineers and teams feel genuinely empowered to hit the pause button, to push back on a rollout if they see risks without fearing negative consequences, especially for changes with a potentially large blast radius.
Giving engineers that psychological safety to say, hang on, this feels risky based on their expertise.
It's absolutely vital for preventing these kinds of incidents, and it ties right into that quote that really stood out from the analysis. A single null pointer shouldn't bring the cloud to its knees. It's such a concise way of saying, look, our foundational systems need to be built with enough resilience, enough defensive layers, that one mistake, even a basic one, can't cause this kind of catastrophic cascade.
That really lands powerfully, doesn't it? Speaks volumes about the level of fault tolerance needed at the heart of these platforms we all depend on.
It really does.
Okay, so let's quickly pull the threads together. We saw how a seemingly minor slip-up, an automated update creating blank data, triggered a fundamental coding error, a null pointer crash, and how that error, because of missing safeguards like feature flags and insufficient defensive code, cascaded globally, taking down core Google Cloud systems and impacting major internet services.
And we looked at the fixes Google's putting in place. Better processes with feature flags and tiered rollouts, stronger code resilience, more robust error handling, and improved communication during outages.
And critically, we've distilled the lessons for everyone using the cloud. The absolute need for multi-region design, planning for graceful degradation so your app doesn't just die, monitoring your platform dependencies, and actually practicing your own outage response drills.
Yeah, this whole event really serves as a pretty significant wake-up call. It highlights that constant tension between speed and safety in the tech world, especially when dealing with the infrastructure that underpins so much of modern life.
Which leaves us, and you, with maybe this final thought to chew on. We just saw how incredibly interconnected everything is. How a single, almost simple data error, a null pointer, could ripple outwards and cause such massive disruption across so many services we use daily. Given that, what does an incident like this really tell us about the potential underlying fragility of these immensely complex digital systems that we rely on almost implicitly for nearly everything we do? Something to think about.